Good evening, and I'll welcome everyone to the Exploratorium and to Everything Matters, Tales from the Periodic Table. Tonight, we're doing sulfur, kind of an important element, actually, very common element. We hope that you have been here before, and we hope that you received your sulfur element card. Does everyone get their sulfur card? Excellent. I want to ask how many people have been to an everything... Oh, thank you, Fran. How many people have been to Everything Matters previous to sulfur? How many have been to hydrogen or helium or lithium or beryllium? Or you can collect them all. I think a lot of them are on the back table over there. So you should get the whole set, because then you can build on your wall a periodic table. It's only going to be another 10, 15 years before we finish out the series, but it's job insurance for me. So just again, blatantly commercial. We actually have calendars for Everything Matters for 2017. So we have little calendars and big calendars. We hope you'll get them at our store. This talk is about 60 minutes. We're going to have two pieces. I'm going to talk a little bit about the chemical properties and physical properties of sulfur. And in the second part, we have a guest, Elton Cairns from the UC Berkeley, Lawrence Berkeley National Labs. And he's going to talk about something that actually is very near and dear to my heart, which is a new technology in batteries, lithium sulfur batteries. Now, how many people have an electric car? Just curious. Oh, a few people. Good. Well, we want one of these batteries in our car, and he's going to tell us why. So that's going to come after me. So let's just get started here. Sulfur is kind of it's a beautiful element, actually. We have some on the front table here for those of you who want to come up and play with sulfur after. I was going to pass it around, but if you touch this sulfur, your hands are going to smell like matches for about 5 days. And it doesn't wash off. So I figure I'm just going to let you come up and touch it yourself voluntarily instead of requiring you to pass it back. It's a beautiful yellow element. Although we may see a different color tonight, if we're lucky. It's element number 16 in the periodic table. You can find it right about there in the periodic table. Let's zoom in on it. So it's the 16th element. The 16 is its atomic number. It has 16 protons in its nucleus and various numbers of neutrons. We'll talk a little bit about that. It's part of the group in the periodic table that we call the oxygen family, because it has oxygen at the very top there. And so, it's also called the chalcogens. So, and sulfur's right there, the yellow one. And as you can see, we have more of those oxygen families coming up in future Everything Matters: selenium, tellurium, polonium, and livermorium. So got that new name down there, that new element. So that's kind of fun. I always like to give a little history of discovery of elements, but sulfur has been known for so long that there is no discoverer of sulfur. You can even go back like to the Bible in Genesis. Then the Lord rained down burning sulfur on Sodom and Gomorrah from the Lord out of the heavens. It's a pretty early mention of sulfur, actually. It also makes it into Revelation. And the devil who deceived them was thrown into a lake of burning sulfur where the beast and the false prophet had been thrown. They will be tormented day and night forever and ever. Nice book. It's one for the kids at night. Okay. If we do want to talk about discovery there, we could talk about Antoine Lavoisier. He actually, in 1777, tried to convince the scientific community that sulfur was actually an element and not a compound. So that's kind of where we might start a kind of modern-day discovery of sulfur. It's a pretty abundant element. If we look at the abundances, sulfur is the 10th most abundant element in the universe. That's pretty high up there. In the sun, not surprisingly, it's also the 10th most abundant element, since the sun is kind of made out of the stuff the universe is made out of, although the sun is a not made out of the original material from the universe. The sun is made out of things from that come from other stars that have exploded in the past. Now, if we move a little bit farther closer in to meteorites, sulfur is a really, really common thing in meteorites. It's the 5th most abundant element in meteorites. In the crust of the Earth, it's about 15. In the oceans, it's about the 6th most abundant element. And in humans, has a surprisingly high, it's number 8 in humans. 0.2% of you is sulfur. Now, some of the interesting things about sulfur is it comes in different forms. We've talked a little bit about this before. Different forms of the same element, where you build the atoms up differently, are called allotropes. And this form of sulfur that we have down here is one of those allotropes. This is where you have sulfur with 8 sulfur atoms in a ring. Kind of looks like this. It's 8 sulfur atoms, kind of a crown-like ring, zigzaggy ring. However, if you heat up sulfur, you can break that ring apart. And I want to do that for you right now. I have some sulfur in a test tube right here, and I have a very hot air blower here. And maybe we can get our handy cam person so you can see it better. Let's see, if I use the calendar as a background, that might work really well. So maybe, okay, so let's see if we get that up on the screen. There we go. So I'm going to turn on the blower. It's kind of noisy. It's a really hot air blower. Let me loosen the cap here. Let's keep the lights up all the way, please. Oh, maybe not. I'm going to zoom in on that. Right now, the sulfur is a kind of a yellowy powder. It's that 8 atom ring of sulfur, and it's going to melt. It may take a little while, so I'm going to have to use some patter here. Okay, so it's beginning to melt a little bit. You can see at the bottom there. It's still yellow because it's just melting. Now it's still those rings of 8 sulfur atoms, even though it's going to turn into a liquid here. And I'm just going to keep rotating the test tube so I kind of heat it up all the way around. But as it breaks the rings apart, the rings will stretch out. Now you can see it burnt. Now it's melting really well. Still a yellow liquid. But this has to heat up to quite a high temperature. Sulfur actually melts pretty low. Sulfur melts at 115 degrees Celsius, so just above the boiling point of water. Yeah, it's beginning to boil a little bit there too. Boils at about 444 degrees C. But you'll notice that the color is going to start changing here. And it takes a little while for this to happen. As the rings break up and form long chains of sulfur atoms, at the very end of the chain, you have free electrons at the ends of the chain, and I'll show you a picture of that in just a moment. I realize that, notice that it's changing color a little bit now. It's turning a little bit more orange as it begins to melt and boil. Can you see the orangey color yet? It'll get better because those long chains of sulfur atoms, it's a different allotrope of sulfur. There we go. We're getting pretty good and melted there. Can I see if I hold that behind? You can maybe be able to see it a little bit better. Maybe not. Maybe it's better without that. See, we still have some unmelted sulfur in there. But it's beginning to turn a little orange now. It may not be just quite visible there, but I can see it right here. It looks pretty orange. And as those long chains of sulfur atoms form, we're going to get this different form of sulfur. It's turning pretty orange now. Can you see that out there? If we keep going, it actually will turn almost a blood red. I don't know how much time we have to do that, but actually, I was going to put on safety glasses for this. I forgot about that. Oops. And as you form those long chains, they get tangled up. And so the viscosity of this liquid, when it gets really red, is not going to be very, you can see right now it's pretty liquidy at the top, but as it turns into this red allotrope, it's going to become more and more viscous. Now it's turning really nice and red. And now we're seeing that other allotrope. That's kind of pretty. And actually, if you look at it, it's not, you see it's not flowing either. It's very viscous now. So this is a different form of sulfur. I don't get to demonstrate allotropes very often live. That's kind of cool. Very viscous. Beautiful red color too. Okay, I think we'll probably beaten that horse into submission. So let's put this, thank you, chemistry. There you see a little bit of the red allotrope at the bottom of that tube right there. And I'm just putting not S8 but SN because these form long chains of arbitrary numbers of sulfur atoms. Well, there they are. With the end ones with their electron. You know what I didn't anticipate? I have hot sulfur in my hand now and I have nowhere to put it. I guess I'll just hold on to it. Those end atoms are what's giving it the red color. And it's going to lose that red color pretty quick and turn back into the S8 rings. And you'll see it'll turn powdery again. I'll just keep it up here so you can see it as I continue to talk. So where does sulfur come from? Sulfur, there it is made in stars, both large and small stars, and it's made at a depth where the temperature is about 2.5 billion degrees, so it has to be pretty deep down into the star. And it's made by fusion. It's made by taking an atom of silicon, and you add to it, you hit it with an alpha particle. It's turning less orange now, too, and it's turning less viscous, too. It can now spill around. Interesting, huh? You don't see things normally when they cool down, they become less viscous. Sure. There we go. Thank you, Herb. So if we hit a silicon atom with a helium nucleus, an alpha particle, bang, it adds it to the silicon atom and it becomes sulfur 32. So you can see all those numbers add up there. Silicon 28 plus a helium 4 gives you a sulfur 32. And that's just one of the forms of sulfur. It's a stable form of sulfur. Here are all the different forms of sulfur that are known. Always 16 protons in the nucleus, but different numbers of neutrons adding up to that number that you see there. Everything from 26 to 49. But there's only 4 of those that are stable, that are not radioactive. These are the 4 ones that are not radioactive. Sulfur 32, 33, 34, and 36. All the others are radioactive. So these are the only ones that you're going to find in nature. The radioactive ones have fairly short half-lives. The longest half-life of any of them is sulfur 35, the missing one in that row, and that has a half-life of only 87 days. So in the age of the Earth, there's not going to be any more sulfur 35. It's just going to all decay. So these are the only ones that you're going to find in nature, and the proportion that you find them in is this. It's mostly sulfur 32. 94% of it is sulfur 32, and then much less of the others. And those are isotopes, as opposed to allotropes. These are isotopes. So the density of sulfur, something we always have to talk about, is about twice that of water, 1.96 grams per cubic centimeter. Water is just 1, and there's a few more elements down there that you can look at. I have density cubes down here. For those of you who have not been here before, you want to test out density, how much stuff is in a given volume. There's a bunch of cubes that are more or less all the same size down there. So come up, there's wood and plastic and magnesium and aluminum, copper, iron, lead, and there's a outsized brick of tungsten that I can't machine, so it is what it is. Come up and check those out. Those cover a very wide range of densities. So here's kind of a density scale. We start at the top with tungsten, and then there's lead and iron and copper and aluminum and magnesium, and there is sulfur way down near the bottom. Sulfur is not a very dense element. Its atom kind of looks like this. The outer electrons is 2 spaces there that don't have electrons in them, so it has a valence of -2, one of the valences. Apparently it'll act with many different valences, but normally those 2 missing electrons give it a valence of -2. It's kind of a small atom too. Compared to a hydrogen atom, it's only a little bit bigger. Its spectrum is, well, just not really remarkable, but there it is. There's the spectrum of mercury. There's not really strong colors in mercury that, like you have yellows in sodium, and hydrogen has only 3 colors, but this has lots of colors, but there's no real distinctive colors that stick out there. Last time we talked about one of the applications of sulfur is in matches, and these guys right here. And as a matter of fact, this is where most people get learn about the smell of sulfur, is in matches. If you light a match and smell, I don't know if you'll be able to smell that. That smell that you get from matches is the smell of the sulfur burning. And matches have an interesting chemical reaction. When you strike the match on the strip right here, this strip has phosphorus and kind of ground glass. And in the match, there's also ground glass and some phosphorus. And when you grind them together, that converts a little bit of the red phosphorus in the match to white phosphorus, which then gets very hot in air and creates phosphorus pentoxide. And it gets very hot in air, and there's another chemical in the match head called potassium chlorate, which is an oxidizer, produces oxygen when you heat it up, and that oxygen then combines with the sulfur, there we go, finally there's sulfur, into sulfur dioxide. So that's the reaction that happens in the match, and everything then goes up in flame. So I don't get to use that transition very often. I have to take advantage of it. It's responsible for the smell of eggs, onions, garlic. That match kind of sulfury smell gives you the smell of all of these food products. When you burn sulfur, which I am not allowed to do, sorry, sulfur burns with a beautiful blue flame. So actually you can see there's the red allotrope of sulfur after you heat it up. But when you set it on fire, it makes this beautiful blue flame. So what I want to do is actually take you on a kind of a tour. I never get to do a geography thing, or a rock music thing. So we're going to take you on the Sulfur World Tour here to lots of different places. We're going to take you to Alberta, to Indonesia, to Hawaii, Iraq, and Io to go really far. If we go to Hawaii first, anybody who's been to Hawaii, the Big Island you go to Volcano National Park, and you look on the far side of the Haleakala crater, you can see the sulfur on the walls of the crater there. Up on the edge of the crater, though, there's a lot of places where sulfur is actually kind of coming up out of the ground where you can actually walk right up to it as long as you don't have asthma. Here you can see sulfur coming up out of fumaroles. Here's a fumarole right here, and you can see the sulfur crusted around the fumarole. If you look really close, a little bit more closely, that's what a fumarole looks like. And look, you can see the red allotrope of sulfur in there because it's really hot. This is actually a fumarole not in Hawaii. This is in Italy, Volcano, Italy. Back to Hawaii, again, you can just walk right up to these things, and the sulfur is just crusting around all the edges here. So that's actually just native volcanic sulfur. I just picked it up. It is a little bit hazardous there. They do post signs that the fumes can be hazardous to your health because there's sulfur dioxide and hydrogen sulfide there. So you have to be a little careful. It could, if you have a sensitive breathing problem, you have to be careful. And if I can tell you that that the guys you're going to see next are not sensitive. We're going to go to Indonesia next, and there's a volcano in Indonesia where these guys actually mine sulfur. And these guys apparently have no trouble breathing in sulfurous fumes. This is a volcano, Ijen, in East Java, Indonesia. And these guys go down into the volcano, and you can see it's a lot of sulfur there, and they actually mine the sulfur. This was quite a nice article that was in, I think, The Atlantic fairly recently. Again, it doesn't look like a job I want to go to every day. And there's, again, you can see the red allotropes of melted sulfur there. Kind of pretty. So this is, again, in Indonesia. Moving to Iraq just recently. News story. You may have caught the news story that ISIS set a sulfur processing facility on fire. So here is the sulfur processing facility. There you can see the mountains of sulfur in the background there. And when you set the sulfur on fire, you get this, I hate to use the term gorgeous, but I mean, it's a pretty blue flame, but it's kind of a disaster here, but it's still kind of a beautiful blue flame of the burning sulfur. And here's my favorite picture of this story. This was in, I think in CNN. This amazing picture of a whole field of sulfur on fire and a fire tornado. You've seen our tornado in the back corner over there? Well, you can do it with fire as well. Actually, there's a museum in Switzerland, the Technorama, that has a fire tornado. It's amazing stuff. So where do we go next? Next, we're going to go to Alberta, Canada. And you'll notice as we zoom in here that you'll be able to see this facility very, very, very high up. Right in here, you'll see the scar on the earth. We're going to zoom in much farther, though. That scar on the earth is the tar sands, where they're mining tar sands in Alberta. And the tar sands produce a bitumen. It's almost like it's tar, and it's high sulfur. You have to remove the sulfur and make sweet crude out of it. And what do you do with the sulfur? Well, there's so much sulfur coming out of this, it's not worth a lot. So you pile it up into these giant sulfur pyramids in Alberta. And since you have so much sulfur, it's worth virtually nothing because there's so much of it. But it is impressive. Sulfur with snow on it. How big is this one of these pyramids? If you just look at one of these pyramids, it's actually bigger than the Great Pyramid at Giza, Cheops. So it's not as tall. It's not as tall as the Great Pyramid, but it has a much bigger base. And the base, of course, is where all the mass of the pyramid is. And so it actually has a larger volume. The Great Pyramid itself has about 2.5 million cubic meters of rock. The Great Sulfur Pyramid of Alberta has about 2.8 million cubic meters, and it's still getting bigger as they mine the tar sands more and more. Those pyramids are growing. So moving out, let's just move out to out in the solar system to a moon of Jupiter. This is Io, which is the innermost moon of Jupiter. And you'll notice it has an interesting color to it. Jupiter's moon, Io, is the most volcanically active body in the solar system, and most of those little round things and those little black scars you see are actually active volcanoes. On the Earth, there's an average of about 7 or so active volcanoes at any given time. Io is just covered with them, And you can see, let's see when that volcano comes around here. This large one right here, notice it has a red, there it is, that has a big red ring around it. That's because there's that allotrope of sulfur around it, but it's virtually all sulfur. It's quite amazing. Io is quite large, by the way. If you compare it to the Earth and to the moon, it's about the same size as the moon, maybe a little bit bigger than the moon. Here's kind of a Mercator projection, and there's that large volcano there with the red ring around it. That's, I think it's called Pele. That's just part of the planet. We can look at the rest of it and look at how many, I mean, it's just amazing. If you see these volcanoes, as the spacecraft passed by Io, it actually photographed lots of these volcanoes actually erupting. You could see them on the edge of Io actually erupting. So you can see down here, you can see a volcano erupting, and here's a little zoom in. And this is looking from above. You can see here's the shadow of the plume as the sun casts a shadow. This is really an amazing thing. Io is, what's the right word for it? Io is massaged by Jupiter. Jupiter's tides stretch and squish Io and keep the insides molten. And so Io is the most active volcanic body in the solar system. Two last pictures. Here you can actually see see this glowing red, an active volcanic front, and you can see the whole surface is basically covered with sulfur. Just one more. You can see all the lava flows here, basically sulfur flows. And if we back off, just look at a diagram, here's Io. Because of the magnetic field of Jupiter, there's a big tube of current, ions flowing around Io, but Io also leaves behind it sulfur atoms in a ring. Io loses about 1,000 tons of sulfur every second, leaves it in this ring. Now, does anybody remember 2010, the Space Odyssey? When they went back to Jupiter to go and look at get the Discovery spacecraft, do you remember what it was covered with? It was covered with, accurately, it was orbiting Io and covered with sulfur. So 2010 got it right. There's lots of chemical compounds that I'm not going to discuss that contain sulfur: sulfide, sulfates, sulfates, and anything that starts with thio has sulfur in it. Just a couple quickies. Sulfuric acid, very important industrially, H2SO4, something that is used all the time around here because we have mosquito problems, malathion, and this is one everybody is actually familiar with, calcium sulfate, gypsum. It is very central in gypsum board or drywall. That chalky center is all gypsum. But if you find it in nature, let me show you it in nature. Here's some crystals of gypsum in nature, but you don't quite get the whole scope because I'm zoomed in a little bit. Let me zoom out, give you the scope of these crystals. See the person right here? That's a person. This is a cave in Mexico, the Cave of the Crystals, and it's pretty dramatic. Those are big crystals. Alum is another. This is a crystal of alum. That's also a sulfur compound. And I have some down on the table here. You come up and take. Oops, I didn't mean to do that. On the table, we have some minerals. Iron sulfide is pyrite, fool's gold. Comes in several forms. It's these beautiful cubes. And of course, I'd be remiss to say that you can actually get these at the store if you wanted them. Pyrite. Here's a pyrite. This is called a pyrite sun, just a different form of crystal formation, probably formed between layers of things. And then there's this beautiful peacock ore, which is a copper iron sulfide, and it's called peacock ore for obvious reasons, beautifully colored. And I mentioned that meteorites have a high sulfur content. So here's one of those, this is a sliced piece of a meteorite that is called a chondrite that has a high sulfur content, about 2.1% sulfur. So it's actually a pretty high percentage of sulfur in this. Can be as much as 6%. There's another form of meteorite, which is an iron meteorite. They don't have as much sulfur in them. And I just want one art use of sulfur I found that's really cool is you can engrave furniture and then pour molten sulfur into the engraving, and you get this sulfur, something called a sulfur inlay. It's really kind of pretty. So that's all I have for right now. Don't go, because we have a really interesting talk coming up. We have Elton Cairns coming up in just a moment. We're going to wire him up, and we're going to talk about lithium sulfur batteries. If you're afraid of your phone blowing up, he has the solution.